Hi, and welcome back to the next physics lesson online. Today we'll be discussing magnetism. There's very little you need to know in the Regents Physics curriculum anymore about magnets. We will only basically discuss the bar magnet, the horseshoe magnet, and the shapes of their fields. So let's get started. What causes a magnetic field around an object? And it turns out that a magnetic field is created by any moving charged object. The picture we have here right below is actually the magnetic field of a bar magnet. It's a piece of metal. Here's a north pole, here's its south pole, and the flow of this magnetic field, which is given the symbol B, which you will not need for any Regents problems, is from north to south, very similar to the way the positive flows to the negative in an electric field. Even though we won't be getting into much of this detail, a magnetic field is created around any moving charged object. So in an atom, since the electron is revolving in the electron cloud around the nucleus, that movement of the electron causes or develops an electric field unto itself. Some metals are naturally magnetic, and that has to do with the extra electron that is uncancelled because of a different electron spinning and creating its own magnetic field. Sometimes the magnetic fields don't cancel out and you get a net magnetic field, which is why certain elements and metals like magnesium and iron are what we call ferromagnetic. Some materials like iron, nickel, and cobalt have a single electron or a pair of electrons that spin in the same direction, creating a magnetic field or a small atomic magnet. And what you see here is the revolution of these charges around the nucleus, and thereby they create a north pole coming out in the direction of this arrow. So now we are looking at a larger size out of the atomic realm, but more in the macro realm. And here we see that the atomic size magnets line up to create domains within the material. So these little domains, one here is green, for example, and the other ones are white with these red arrows pointing in different directions. These red arrows represent north and south, like little compasses. And a metal that is unmagnetized has this random separation and random pointing of all of these little internal atomic magnets. Now, it's not until the individual domains line up, so the arrows point in the same direction, do we actually get a true north pole. There are several ways that these magnetic domains can be rearranged, and usually the easiest way is when a piece of metal sits in a very strong magnetic field. All these atomic domains align with it. So here we have all the arrows pointing to the right. So this side would be the north pole, the arrowhead side. And then, of course, the flow would be around and back into the south pole. Now, inside the magnet, they flow straight through. And this is a picture of the bar magnet. Here's the north, here's the south, and this is a little diagram describing the arrangement of the magnetic domains within the metallic structure. So a magnet has two ends called poles, and a magnet has dipole, meaning two poles, where the magnetic force is the strongest. We have the north and the south, and no matter how many times you break a magnet, each piece always has a north and a south pole, because when you crack this metal in half, while this part is more north than this part, once you crack it right here, this part is further away from the North Pole and is south. And of course, this part, which was the truest south, this part is closer to the north. So breaking a magnet in half, you actually get two smaller magnets with weaker intensity, but you can never separate a North Pole from a South Pole. There is no such thing as a magnetic monopole, but there is such thing as an electric monopole, being plus or minus. And when you bring a plus and minus near each other, you get an electric dipole. But in the case of magnets, you never have a magnetic monopole. It doesn't exist in nature. As we said in earlier lessons, a field is an invisible zone of influence that exists around an object. So a gravitational field is the gravitational influence on objects near it. An electric field is an electric influence on charges. And here we have again a magnetic field which exerts influence on metals or other electrons or other protons, which we will touch on slightly but not get much into anymore in this curriculum. So a magnetic field exists around a magnet or any moving charged object. Magnetic fields are like electric fields or gravitational fields in that they allow interaction without touching. The invisible zone of influence. Interact without touching. Just like with electric fields and gravitational fields, we use a drawing to demonstrate the direction of flow of the field. So the magnetic field line or the flux line, which literally means the flow line. So here we have the picture flowing from north to south on the outside, and then through the middle it would have to return back again to north. All right, let's talk about the rules for drawing magnetic fields. And they are the same as the rules of an electric field. The magnetic field lines always go from north to south pole. The electric field lines always go from positive to negative, so they are analogous. Here is a bar magnet. If we follow the flow of the magnetic field around on the outside and back again, we go from north to south on the outside and south to north on the inside. It's a continuous flow. It actually never stops. If we take this bar magnet and we bend it into the shape of a horseshoe or the letter U, the field on the outside of the magnet from north to south makes the traditional curves, but on the inside, between these two parallel bars of north and south, this is analogous to the parallel plate electric field, and you have a flow from north to south, and all the lines are parallel to each other on the inside, which I hope you remember means that it's a uniform strength field. And so when the lines of flux are evenly separated, you have the same magnetic force acting on the charge. When they're on the outside, they have varying force because the lines are not the same distance apart. The direction of the magnetic field is determined by using a compass. The needle of the compass points in the direction of the magnetic field. So let's take a look. Sprinkle iron filings on a piece of paper, and we lay down a series of compasses. As you see here, the needle of each compass is slightly tilted compared to the one before it. And then as you flow around, this needle changes complete direction. But the flow is always from north to south. North to south. So in this case, we have north here on the red side, and it points away and curves, pointing away and curve, pointing away and curve, and boom, back to the south side. As you can see in the diagram where the lines are drawn, you can see the little tiny compass needles right here. That's what these little triangles are. It's flowing around and back again. So that is the standard magnetic field of a bar magnet, and soon you're going to see of the Earth as well. Just like electric fields, magnetic field lines are closed loops and they never cross or intersect. And the reason is very simple for that. They don't cross or intersect because each line represents the resultant of a vector. So it's always following the tangent to this arc, and then it comes back in again. So closed loops, which never cross. Okay, here's the next rule. And it is the same as the electric field rule. When the magnetic field lines are closer, the magnetic field is stronger. That is the exact same rule for electric fields. When electric field lines are closer, the field is stronger. But now we're dealing with magnetic field lines. So you can see that the concentration of the lines, or the flux density, as we would call it, decreases as you move away from the source and increases as you get back to the other pole. So you have north around to south. The lines are very dense right here at each of the poles, and then as you move away, the wings of this butterfly spread out, the field lines get further apart, and therefore their intensity decreases. But as you get closer to each of the poles, the lines converge and they get stronger. The magnetic field strength is given by the letter B, and that's actually equal to the force per moving charge. This is a very interesting formula, which is no longer in the Regents curriculum. It's now in the AP curriculum only. But this magnetic field intensity is equal to the force per moving charge, not just force per charge, because you have a velocity right here, Q times V. So it's force per moving charge, because you have to have a charge moving through the field in order to be acted on by the force. But the general point is this: the number of magnetic field lines of flux per unit area passing through a plane perpendicular to the direction of the lines is called the magnetic field strength. So these blue lines all represent the magnetic field, and this ring, this circle right here, is an area that can be measured, and then the number of field lines that pass through that is the flux density, and you can see the strength of the field. So if there are more lines in this circle, then it's a stronger field. If there are less lines in the circle, it's a weaker field. And the Weber per square meter, see, meter squared is an area here. That's what we call the Tesla. Many of you know the car, the Tesla. Well, before there was the car, there was the man himself who gets the credit for putting a lot of this information together for us. Teslas are used for the unit of magnetic field strength or magnetic flux density. If a charge is moving along these blue lines along the field, it does not experience any force, but if it tries to cut across these lines, then it will feel a magnetic force. And finally, we have the law of poles. Opposites attract and similar repel. So north attracts south, and north-north, south-south are repulsive. And finally, in closing, we have the magnetic field around the Earth. So here's the Earth's north pole, and this is the compass, which is always pointing around from north to south. So it actually turns that the Earth's magnetic field is upside down. So magnetic north is really geographical south pole, and magnetic south is really at the Earth's geographic north pole. So a compass needle will always point from north to south, and that's why our red pointer right here on the compass needle will always flow in this direction, the red pointing towards the geographical north. It is known that the Earth's magnetic fields do flip around every 15,000 years, and this is something that was discovered through the studies in earth science and the studies surrounding the mid-Atlantic ridge and the reversal of magnetic domains in granite rock at the seafloor. The last thing we would like to tell you here is that the Earth's magnetic field is our umbrella against the sun's cosmic rays. All of the solar wind that comes from the sun is directly shielded by the Earth's magnetic field, and this is the source of the northern lights. This is the end of the introduction to magnetism, and sadly the end of what is presently required in the Regents curriculum. Thank you for watching.